Okay. So right, so let's get back to it. We've shown that G is isomorphic to C4 as long as we fill this gap. So let's fill that gap right now. Because what we did, we showed that if phi of x equals the identity, then x equals the identity. Okay, and what we should have really showed is that phi of x equals phi of y implies x equals y. Okay. So what we have to do, we'll gather up all the x's. Yeah, we'll show like a more general property. So we have a definition. Let's take a homomorphism from G to H. Okay, and we'll define the kernel of the homomorphism. This is called the kernel. Okay, let me just see. The kernel of phi is going to be all the elements of G which map to the identity of H. So this is a subset of G. It's all the elements in G, such that phi of G is the identity of H. And the kernel of phi has a lot of nice properties. Okay. Let phi from G to H be a homomorphism. Kernel of phi is a subgroup of G. The kernel of phi is the identity, exactly the identity of G if and only if phi is 1-to-1. In fact, actually, the kernel of phi is a normal subgroup of G. Okay, and let's just prove part B because that is the main one we're interested in here. Proof of B. Suppose phi is 1-to-1 and G is in the kernel of phi. Now the kernel of phi is all the things such that phi of G equals the identity. And the identity is, we know that a homomorphism sends the identity of G to the identity of H. Now phi of G equals phi of the identity. Phi is 1-to-1, so G equals the identity. Oops, since phi is 1-to-1. Okay. That proves that the kernel consists exactly of the identity of G. Okay. So if phi is 1-to-1, then the kernel is kind of the trivial subgroup. Okay, let's suppose that the kernel is a trivial subgroup. Let's also suppose phi of G equals phi of G prime. And we have to show that G equals G prime. Okay. Then phi of G inverse G prime. What is that? Well, that's just phi of G inverse times phi of G prime. Phi of G inverse is just phi of G inverse. Or actually, no, let's do it like this. Phi of G prime is the same as phi of G. That's because phi of G equals phi of G prime. Now phi of G inverse times phi of G, that's just phi of G inverse G. G inverse G is just the identity of G. Phi of that is the identity of H. Okay. So G inverse G prime is in the kernel of phi. The kernel of phi only has one thing. Okay, so G inverse G prime equals the identity. Multiplying on the left by G, you get G prime equals G. Okay, that shows phi is 1-to-1. Okay, so now we've really shown that for a homomorphism, being 1-to-1 is the same as checking if the kernel is the trivial subgroup, which is kind of the point we skipped over in our proof. Okay, and that is why we have kernels, so that instead of checking like phi of G equals phi of G prime implies G prime equals G, we can just find what the kernel is. Okay. So that's the end of the proof of B, which we wanted to do. Okay. Now we have to finish off the proof of our theorem. Wait, this thing is giving me problems again. Okay, back to our theorem. Let me remind you what we have to show. We're in the following case. G has no element of order 4. But G has 4 elements. And our goal is to construct an isomorphism phi from our group V to G, where V is this group with 4 elements. Okay. Okay, so since G has no element of order 4, we can write G is the identity in X, Y, and Z such that Z is going to be XY is YX, and X squared equals Y squared equals Z squared. Okay. Oh, and that's supposed to be the identity. The reason is we just go through the same argument we already saw when we were constructing V. Okay. Right, and remember, we know that there's 3 non-identity elements because there's 4 elements in all, and all the non-identity elements have order 2. Okay, so we get this, and then some like the cancellation law and stuff like that implies that X, Y has to be equal to Z, and then because Z squared is the identity, you get X, Y equals YX. Okay, so now we're going to define phi from V to G by phi of A equals X and phi of B equals Y. Now, because A and B generate V, that's all I need to tell you is that phi is a homomorphism satisfying these 2 things, and then I need to check that all the equations of all the relations of V are satisfied when I plug in these 2 values. So we need to check. So for phi to be a homomorphism, we need to check phi of A squared equals the identity, phi of B squared equals the identity, phi of AB equals phi of BA. If all these things are true, then phi will be a homomorphism. Phi of A, that is just X. Phi of B, that is just Y. So this is Y squared is the identity. And phi of AB, that's just XY. And all of these things are true. Okay. So phi is a homomorphism. Also, phi is onto, right? Phi of the identity is the identity. Phi of A equals X, phi of B equals Y, and phi of AB equals XY, which is Z. Okay, so phi is onto, phi is a homomorphism. Oh yes, I'll flip back to the previous page for like a minute. Okay, now I will flip back. Okay, so now phi is a function that is onto from two sets of the same, which between two sets of the same size. So it's automatically 1-to-1. Phi is 1-to-1. So that tells us that G is isomorphic to V as we wanted. Okay. Oh yeah, I guess I should make a note before I end. We can see V is not isomorphic to C4, right? Since if phi goes from C4 to V, we'll have phi of A will be in V. Everything in V satisfies x squared equals the identity. So phi of A squared equals the identity. That implies that phi of A squared is the identity. That means A squared is in the kernel of phi. So whenever you have a homomorphism from the cyclic group with 4 elements to V, there's this element in the kernel at least. Okay, so phi can never be 1-to-1. Okay. So there is no isomorphism between a group of order 4 or the cyclic group of order 4 and V. Okay. So now we have our complete list of groups of order 4. Well, it's just 2 things. And they're both pretty a little bit simple, but that's okay. Now we are done with the theorem. Okay. Let's talk about one more example about generators and relations. Define G to be generated by A and B. And let's see. I'll say like A to the 4th is B squared is the identity, and BA equals A squared B. Okay. And let us show that G is actually just trivial. Okay. So sometimes, I mean, when you define a group, you can just say whatever generators and write down any relations you want. But sometimes you can write down relations which kind of make the group uninteresting, right? Okay. So let's work with BA equals A squared B. Okay, one thing to do we might try to let's try and multiply on the right by B. Then we get BAB is A squared B squared. B squared is the identity, so we just get A squared. Now, A to the 4th is the identity, So let's try taking this equation and squaring both sides. We have BAB equals a to the fourth, which is the identity. Now, if we simplify this, we get B squared is the identity, AB. We get BA squared B is the identity. But A squared B is BA. So B squared A is the identity. B squared is also the identity, so A equals the identity. Actually, I was wrong. I should have said, show that G equals this. This relation disappears because this generator disappears. And this equation just becomes B equals B. This still becomes B squared equals the identity. Okay. So you just have, so G is just the cyclic group generated by B, satisfying B squared as the identity. Okay. So depending on what relations you write down, it can really affect the structure of the group. Okay. Okay. So let me modify this this slightly. Let me change this 2 to a 3, and that will be our new example. We'll call this what should I call this? We'll call this D4. This is going to be generated by A and B. A to the fourth is the identity, B squared is the identity, and BA is A cubed B. Okay. First, because we only have 2 generators, and I have this rule which allows us to switch them. Like if I have a big long string of A's and B's, whenever a B comes before an A, I can switch the B and the A, right? But with this rule. Okay, so notice every element of D4 can be written as A to the J times B to the I. Let's just convince ourselves of that on the next page. Let's write just here's what an element of D4 might look like. It might be like A to the fifth, B, a to the minus 3 b squared, and then it might be like a b inverse, and then we might have an a to the 6th, and then I might have a final b, and that's it. This is what an element of D4 might be. And I want to see that I can rewrite it as a to some power, b to some other power. Okay, and the key is the b's, I want to move all the b's to the right and all the a's to the left. Okay, so we can start with this. This b needs to switch with this a to the minus 3. Okay. So first of all, a to the minus 3 is a. Why is that? Well, a to the 4th is the identity. So a times a cubed is the identity. So a multiplying by the inverse of a cubed, we have a equals a to the minus 3. Okay. So this, we can rewrite this whole thing as a to the 5th ba, b squared, a b inverse, a to the 6th b. And now I know that b times a is a cubed b. Okay. So now I have a to the 5th times a cubed. I have b times b squared. So b times b squared is really b cubed. A times a to the 5th times a cubed is really a to the 8th. Okay. Now remember, in my definition of D4, I have these relations. I have the relation a to the 4th is e, b squared is the identity, and I have ba equals a cubed b. Okay, so if a to the 4th is the identity, then a to the 8th is a to the 4th squared. So that's just the identity. B squared is the identity, so b cubed is just b. So you get b, a, b inverse, a to the 6th b. Now ba is just a cubed b. Okay, now b times b inverse is just the identity. This is just a to the 9th. Now a to the 9th is a to the 8th times a. A to the 8th we already saw is the identity, so we just have ab. Okay, and so you can see, like, no matter what crazy string of a's and b's and a inverses and b inverses, just using these three relations, I can always move all the a's to the left and all the b's to the right. Okay, and using these two relations, my power of a is going to be either a to the 0, a squared, or a cubed. My power of b is just either going to be b to the 0 or b to the 1. Okay, so this procedure tells us every element of D4 can be written as a to the I, b to the j, where I can be 0, 1, 2, or 3, and j equals 0 or 1. Okay, so in effect, D4 has 8 elements, has the identity a squared, a cubed, and it has b, ab, a squared b, a cubed b. And we also, like, how would we multiply any two elements? Well, we just use the rules we just talked about. Like if I want to do ab times a cubed, well, to go slow, I might write it as ABAA. I might switch A and B, B and A with A cubed B, and I do the same thing. And I do the same thing again. And then I stop. Now I have A to the 10th B. A to the 10th is really A to the 8th times A squared. A to the 8th is the identity. So I have A squared B. Okay. And notice to compute, when I had to do B times A cubed, I could have just written it. It turns out it was just BA cubed is just AB. The A to the J is just A to the 4 minus J B for all J. Which gives us a more general rule to switch A and B. So this gives us enough information to work out multiplication in D4. Okay. And before we leave, we can define a more general group. Dn is going to be generated by A and B. It's going to satisfy A to the n is the identity, B squared is the identity, and BA is A to the n minus 1B. Okay, so let's again take another 5-minute break. And when we come back, we'll just look at some of the basic properties of Dn. Oh, yeah, I can flip back very, very quickly because there's only 30 seconds left in this session. 2 pages. Okay. So I'm gonna, but I have to end it in about 5 seconds, just FYI. Yeah, okay. So I'm restarting now. Okay, bye.